Okay, this is solving equations. You will need your copy of the unit circle to do this. Okay, very, very basic trig equations look like the first two at the top of the page. Sine x equals negative root 2 over 2. Sine is the y coordinate around the unit circle, so you go around the unit circle, you look for places where the y coordinate is negative root 2 over 2. That is going to happen at 5 pi over 4 and 7 pi over 4. All done. Cosine negative, so this symbol is the Greek letter theta. It's just a variable. It means the same thing as x. So cosine theta equals negative 1/2. Cosine is the x coordinate, so you're going to go around the unit circle and look for places where the x coordinate is negative 1/2. That happens at 2 pi over 3 and 4 pi over 3. Done. So all of the other types of equations we're going to be looking at, the last step will be to get to simple equations that look like this. So for example, the next one down, I want to get the cosine function by itself. So the first thing I'm going to do is subtract square root of 3 from both sides. And then I need to divide by 2. Okay, and then now you go to the unit circle. You're looking for places, it's cosine, so you're looking for places where the x coordinate is negative root 3 over 2. That's going to happen at 5 pi over 6 and 7 pi over 6. This one, again, I want to try to get the sine function by itself. So I'm going to move the 1 over to the other side. Divide both sides by 4. I'm going to take the square root because the sine is squared. Okay, when you take the square root of a fraction, you just take the square root of the numerator and the square root of the denominator. Anytime you're taking the square root, you need to make sure to do plus or minus. The square root of 1 is just 1. The square root of 4 is 2. So we basically get the equation sine theta equals plus or minus 1/2. So we are going to go around the unit circle and look for any y values that are either positive 1/2 or negative 1/2. That is going to happen at all of the over 6's. So positive 1/2, positive 1/2, negative 1/2, and negative 1/2. Okay. The last equation on this page, 2 cosine squared x minus cosine x equals 0. This one begins a type of problem where we're going to factor. Those two terms have a cosine x in common. So when I factor out a cosine x, what's left behind is 2 cosine x minus 1. And now that I have a product, and it's equal to 0, I'm going to set each of these pieces equal to 0 and solve. So cosine x equals 0. That happens at pi over 2 and 3 pi over 2. And then 2 cosine x minus 1 equals 0. Again, get the trig function by itself. Divide both sides by 2. Cosine x equals 1/2. That happens when that happens at pi over 3 and 5 pi over 3. So this solution has this equation has 4 solutions. Pi over 2, 3 pi over 2, pi over 3, and 5 pi over 3. Okay. So the next type of equation you're going to see in this unit is a quadratic form equation. So this is basically a quadratic, and if the trig functions are tripping you up, you can always do this little trick where you let b stand for the trig function, and if we rewrite this, it's 2b squared plus b minus 1. That doesn't look too intimidating to factor, so whenever there's 3 terms like this and one of them is squared, you're going to factor. We're going to have 2b and b. The second term has to be 1 and 1. So the first slots, we're looking for things that multiply together to make 2b squared. Second slot, we're looking for things that multiply together to make negative 1. So we're going to need a plus sign in one parentheses and a negative sign in the other. Trust me, that's how it works out. So now we have a product that's equal to 0, so we can set each parentheses equal to 0. Okay, and now we can plug back in for what b stood for. B stood for sine x. So again, you just go to your unit circle. Now you're looking for places where the y coordinate is positive 1/2. That's going to be pi over 6 and 5 pi over 6. And then over here, you get sine x equals -1. The y coordinate around the unit circle is only equal to -1 in one spot. That's 3 pi over 2. So this equation has three solutions. Pi over 6, 5 pi over 6, and 3 pi over 2. Okay. The next type of equation you're going to see involve what are called Pythagorean identities. So I'm looking at this equation here. So this would be like the problem you're given. And I notice it has two different trig functions in it. There's cosine over here, but then on the other side, I have sine. It's difficult to solve trig equations that have two different types of trig functions in them. It'd be great if I could get the whole equation to either be all cosine or all sine. Well, as it turns out, there are these Pythagorean identities. There's three of them here. If you want to figure out why they're true and that sort of thing, you can look in the packet, but take my word for it. These are all true, and you should have them on your sheet along with your unit circle when you do the test. Notice that they only apply when the trig functions are squared. You cannot use these to replace any trig functions that aren't squared. So for example, in this equation, I can't use these to replace cosine x because that cosine x is not squared. I can use them to replace this sine squared. And in fact, using this Pythagorean identity, I'm going to move the cosine squared x to the other side, and you get sine squared x equals 1 minus cosine squared x. So that means in my equation, anywhere where I see a sine squared x, I can replace that with what it's equal to, 1 minus cosine squared x. So I'm going to take my original equation, -6 cosine x plus 6 equals 4. And now instead of sine squared, I'm going to put 1 minus cosine squared. Okay, so I'm going to do a little algebra. Distribute the 4 to both terms. You get 4 minus 4 cosine squared x. Now that I have all the same trig functions, I'm going to move everything over to the left-hand side and get it equal to 0. So you get 4 cosine squared x minus 6 cosine x, and then plus 2 equals 0. You can factor this. First, you can divide each term by 2. 2 cosine squared x minus 3 cosine x plus 1 equals 0. Again, if you need to, you can let b equal cosine x, in which case the equation becomes 2b squared minus 3b plus 1. Now I'm going to factor. First slot, I need two things that multiply together make 2b squared, so that's going to be 2b and b. In this spot, I need things that multiply together to make 1, so that's going to be 1 and 1. Since this sign is positive, I know that the signs in the two parentheses have to match. And since the middle term is negative, I know that they both have to be minus signs. So, bloop, bloop. Now that I have a product that's equal to 0, I can set each parentheses equal to 0. Excuse me. B stood for cosine x. Cosine is the x-coordinate around the unit circle, and the x-coordinate is equal to 1/2 at pi over 3 and 5 pi over 3. Then over on this side, you get b minus 1 equals 0, b equals 1, cosine equals 1. And the only time that happens is when x equals 0 radians, so right at the start of the unit circle. So this equation has three solutions, and there they are. Okay. So this is probably the most complicated type of problem that we have in this unit. I look at this, I see two different trig functions, cosecant and cotangent. So I definitely want to use one of the Pythagorean identities to convert one of them into the other, so I only have one type of trig function. But like I said on the previous page, you can't do any substitutions unless the functions are squared, and these functions are not squared yet. So our first step is going to be to move the cotan to the other side. We want to make sure there's only one trig function on each side of the equation, because now I'm going to square both sides. Okay, so on the left-hand side, you just get cosecant squared theta. Okay, so this is where most people make their mistake. When you go to square the right-hand side, most people will just square each of the terms and say that the right-hand side is equal to 1 plus cotan squared theta. But actually, you have to FOIL. You have two terms, and there's a plus sign in between them, so you actually have to FOIL this. And when you do that, you get 1 plus 2 cotan theta plus cotan squared theta. All right. Okay, so if we look at our Pythagorean identities, you should have yours on a sheet of paper. But now I can replace, now that cosecant is squared, I can replace it using the Pythagorean identities. So if we scroll up, back to our Pythagorean identities, now we're looking at this Pythagorean identity. Cosecant squared is the same thing as 1 plus cotan squared. So I'm going to replace cosecant with 1 plus cotan squared theta. Okay, now that everything is in terms of the same trig function, we're going to bring everything to one side and set it equal to 0. We get a lot of nice cancellations here. The 1's cancel on both sides. The cotan squareds on both sides cancel. So actually you just get 0 equals 2 cotangent of theta. If you divide both sides by 2, you get 0 equals cotan theta. Cotangent is cosine over sine. If you want to, you can think of multiplying both sides by sine theta. And cosine equals 0 at pi over 2 and 3 pi over 2. Now, anytime you square both sides of an equation in the process of solving it, you create the possibility that one or more of the solutions you get will be false. So we need to check our answers in the original equation. So these false solutions are also called extraneous solutions. So I'm going to take pi over 2 and plug it into the original equation. Cosecant theta is the same thing as 1 over sine. And then cotangent, as I said, is cosine over sine. And we want to check to see if that's actually equal to 1. So sine of pi over 2 is 1. So you get 1 over 1. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. And so you're going to get 1 minus 0. That is, in fact, equal to positive 1. Okay, now let's see what happens when we check the other solution, 3 pi over 2. I'm going to pause it and write it out for a second. Okay, so I just filled some in here. What happens this time is that when you do sine of 3 pi over 2 in the denominator here, you actually get negative 1 instead of positive 1. So you end up with negative 1 minus 0, which is actually not equal to positive 1. So 3 pi over 2 is an extraneous solution. You have to throw it out. There's only one solution, and it's pi over 2. Okay, last type of equation here. I'm going to write some stuff out and explain it. Okay, so I let b stand for 4 theta. So then you get the simple equation sine of b equals 1/2. That happens at pi over 6 and 5 pi over 6. So then you just plug back in for what b stood for. That gives you base solutions of pi over 24 and 5 pi over 24 when you plug back in for b. Now, you need to figure out what the period of this function is. It's pi over 2. For convenience sake, I made a least common denominator 12 pi over 24. you have to add the period over and over again until you get to 2 pi to get all the solutions. All right.